Have you ever stopped to really, truly think about light? I mean, it's just everywhere. It seems so simple, but underneath that simplicity is this whole universe of mind-blowing physics. Today, we're going to pull back the curtain and see how scientists and engineers have learned to tame light with just incredible precision.
So let's start with a question that might sound a little weird. We all know what white light is, right? It's the light from a bulb, from the sun, but what if I told you that in the world of physics, there's not really any such thing?
Because what our eyes actually see as light, all the colors of the rainbow, is just this unbelievably tiny sliver of a much, much bigger reality. You're looking at it here, the electromagnetic spectrum. From super powerful gamma rays all the way to long radio waves, it's all the same kind of energy. Our entire visual world is just packed into that one little band.
All right, so here's our game plan. We're going to kick things off with what light really is. Then we'll get into how to measure it and how it's made. After that, we'll zoom in on LEDs, learn how to control light with filters, and finally, wrap it all up with why any of this precision actually matters.
Okay, first up, what is light, really? Let's get down to the fundamentals. At its most basic, rock-bottom level, light is energy. And that energy doesn't come in a smooth stream. It comes in these tiny individual packets, little chunks of energy. And when one of those energy packets happens to be in that visible part of the spectrum we just saw, we call it a photon. It is literally the smallest possible piece of light you can have. Now, this is where things start to get really interesting, because when we try to measure this energy, we run into a fascinating split. There's the pure physics of it, and then there's how our human eyes actually perceive it. They're not the same thing at all. So, on one side, you've got radiometry. This is pure physics. It just measures the raw energy of the light in watts or joules. It doesn't care about an observer. On the other side, you've got photometry. This is all about human perception. To our eyes, a green light looks way brighter than a red or blue one with the same amount of physical energy. And that's the key takeaway here. The same amount of raw energy can seem brighter or dimmer to us, all depending on its color. Okay, so we know what light is, and we've got two ways to measure it. Now, how do we actually make it? Let's dive into the sources.
In the world of science and tech, there are a few key families of light sources, and you can think of each one as a specialized tool for a different job. You've got everything from old-school halogen bulbs to these incredibly precise laser diodes, and as we're about to see, each one has its own completely unique light signature.
Let's start with a classic, the quartz tungsten halogen bulb, or QTH. It basically works by heating up a little wire until it glows. Now, look at the graph of its light output. See that smooth, continuous curve? It's producing a really broad spectrum of light, kind of like natural sunlight. It's got a little bit of everything.
Now, for something totally different, this is a mercury arc lamp. Check out its spectrum. Whoa! Instead of a smooth curve, it's all of these super sharp, really intense spikes. It's pouring all its energy into very specific colors. This is awesome for things like, say, making biological samples fluoresce under a microscope.
And then, for the absolute ultimate in precision, you have the laser diode. Just look at that graph. It's not even a curve, it's a needle. It's putting out this unbelievably sharp single peak of light. We call this monochromatic light, just one single color, and it's the backbone of countless high-tech gadgets.
Okay, let's zoom in on a light source we all use every single day, the LED, because it tells a really important story about why this whole idea of precision is so critical in science.
So a normal LED, it doesn't make a perfect spike like a laser. Instead, it produces this sort of bell-shaped curve of light that's centered around its target color. It's definitely more focused than a halogen bulb, but it still has a bit of a spread.
But here's the catch, and it's a big one. Take a close look at this slide. This LED was sold as a 465 nanometer blue LED. That's what it says on the box. But when someone actually measured it, its peak, its brightest point, was way over at 476 nanometers. That's a huge difference if your scientific experiment depends on being exact.
And this brings us to what might be the single most important lesson from all of this. You simply cannot trust the manufacturer's spec sheet to be perfect. If you need to be absolutely, positively exact about the light you're using, you have got to measure it yourself.
And wait, it gets even more complicated. You'd think that dimming an LED just makes it, less bright. But check out these curves.
As you turn down the power, the peak wavelength of the light actually shifts. Its color is literally changing as you dim it. This just proves it again. For any serious work, direct measurement is the only way to go.
So, if our light sources aren't always perfect, how in the world do we get the exact light we need? Well, the answer is in our next section. We're moving from just making light to actually sculpting it. Welcome to the art of the filter.
You know those beautiful, shimmering rainbow colors you see on a soap bubble or an oil slick? Ever wonder where they come from? It's a really cool phenomenon called thin film interference. And believe it or not, it's the exact same physics that engineers use to build some of the most sophisticated optical filters on the planet.
Okay, here's how it works in a nutshell. When light hits a super thin film, some of it bounces off the top surface and some of it bounces off the bottom surface. Now you've got these two reflected waves, and they interfere with each other. If their peaks and valleys line up, boom, they amplify each other and you see that color bright and clear. But if they're out of sync, they cancel each other out and that color just vanishes.
And engineers have gotten insanely good at this. By carefully stacking dozens and dozens of these microscopic layers, they can create something called a stop band. Look at the graph. As they add more layers, going from that light blue line to the dark blue one, the filter gets way better at blocking a very specific range of colors, creating that super sharp valley, while letting everything else pass right through. It's incredible control.
So wow, we've gone from the fundamental photon all the way up to these amazing high-tech filters. Let's bring it all together and talk about the big takeaway. Why does any of this precision even matter?
All right, let's recap the highlights. We learned light is energy, and we can measure it based on pure physics or on how our eyes see it. We saw that different tools, bulbs, LEDs, lasers, all create their own unique light signatures. We definitely learned the most critical rule. If you need to be precise, you have to measure it yourself. And finally, we saw how the simple physics of a soap bubble lets us sculpt light, which makes so much of our modern world possible.
Just think about it for a second. The very screen you're watching this on right now isn't producing white light. It's an incredibly carefully crafted illusion, built from millions of tiny red, green, and blue light sources, all precisely filtered and managed to trick your eyes. It really makes you wonder, doesn't it? What other parts of your daily life are built on this same totally invisible mastery of light?